Welcome to this session. Can go ahead and as you join, just go through the quiz. If you've already done it, please indicate in chat that you've completed. Then at 11:35, we shall have Ernest take over as he reviews the quiz before proceeding to the final section.
Okay, so hi everyone, this is group 1 and group 2. So hi to everyone, including those I have not interacted with. So the very first thing we're going to do is go over the quiz, and then we can do something else. So I hope you can see my screen. Can you see my screen? Can you hear me?
Yes, yes.
Okay. So we go over the quiz. The first question: which of the following models can work for categorical variables unencoded? So we realized, we mentioned that as we create models, most of the time they do not understand, actually a larger percentage of the time, they do not understand categorical variables. What we pass into models is numeric values, that is your floats and your integers. However, I know for group 2, we may have not covered this, but we can mention it. So for k-means clustering, you have to make sure that the variables you pass in are in numeric form, as well as for linear regression and for logistic regression. However, for random forest, your variables can take categorical values, because what a random forest tries to do for you is it tries to create something like a flow chart. So if you have categorical variables, that means within your flowchart, that means the flowchart can go either in one direction or the other direction. So you are allowed to have your categorical variables. That is when you're using decision trees and random forests. But for other models, they only accept numeric values. So the second question: each cluster is grouped around there. So when we were dealing with k-means, we mentioned that what happens during the first iteration, if you have not given the optimal number of clusters that you would want, the first thing that happens is what the algorithm plots for you the data, and it creates for you 2 clusters at first, and these 2 clusters are created around centroids. So centroid is the middle point of the cluster. It's what describes what is within that cluster. If it's a cluster of numeric values, then the centroid is probably the mean, because it's what is at the middle of the cluster, and then the other data points are spread around that centroid. So each cluster is grouped around the centroid, and the centroid should be a very good estimation of the mean of the values that are within that cluster. So the third question: what would a k-means model be greatly suited for? So a k-means model, we saw that this is a clustering algorithm. It's actually called k-means clustering. So if you want to find patterns within your data, you want to find clusters within your data, k-means is what you'd want to use. So customer segmentation, this is what you can use k-means for this. Presence of disease prediction. For this is a classification problem. So for this, you can opt to use logistic regression. However, if you're interested also in how the decision was made, the flow of how the decision was made, you can opt to use a decision tree or a random forest. We have weather forecasting. So weather forecasting, if you have defined weather states. For instance, you have raining, sunny, etc., etc. So for that, you can opt to use your logistic regression or your decision tree as well, because it's a classification problem. So for k-means, it's when you're trying to find clusters within your data, you're trying to find patterns, you're trying to group your data points that are similar together. So with customer segmentation, you'd be trying to group similar customers together so that you're able to get some information about them. So for k-means, customer segmentation would be a very good application of it. So on to the next question. A decision tree produces results of greater accuracy than a random forest. So the idea of a random forest is created by many decision trees. So what happens within a random forest is, if the algorithm was just called forest, that would mean a couple of trees. As we're saying, a random forest is made up of many decision trees. However, we have this extra parameter, random. So the idea of random is that the decision trees that the random forest creates for you are based on random subsets of your data. That is, it's going to take a small sample of your data, create a tree from that, and then it's going to take another different random sample, create a tree from that. And also, the variables that determine the decisions you're going to make, that is your independent variables, it also picks some combinations at random, and it gives different importances to the different variables, so that it's able to determine, then the decision that it's going to give you is going to be an aggregate or an average of the output of all the individual decision trees. So all these individual decision trees have been created from random points of data with random combinations of your independent variables. That is, each of them have been given different importances, so that it's able to get an aggregate weight of which variable is most important, which output is the most is the average. So basically, with a random forest, you're bringing very many decision trees together, and on top of those decision trees being many, they have been created from random points within your data, as well with a random combination of your independent variables, as well as with a random combination of your independent variables. So the output you're going to get from a random forest is an aggregate of very many decisions. So that is going to be, it's going to have better accuracy, because it's a better representation of your data as opposed to just one decision tree. So if we were to answer this question, a decision tree produces results of greater accuracy than a random forest. This is false, because within a random forest, the decision that you make is the aggregate decision that has been made by all the decision trees that have been created. Okay. Then we can move. So the answer to this question is false, because a random forest is going to give you greater accuracy, because the decision it gives you is an aggregate, is the mean of all the decisions that have been made by the many decision trees that it created. Move to the next question. Which metric is not part of the classification report? So with the classification report, this is also something very similar to what you have in the confusion matrix. So if you will understand your classification report, you'll be able to understand your your confusion matrix. But also at your own time, those things, those parameters, those metrics that are within classification report and confusion matrix, please try to find out what they mean, because depending on the data that you have and what you're trying to achieve, you will be trying to minimize or maximize or optimize a certain metric that is not that wouldn't be relevant for somebody else. So find out what they are, so that you know what will be important to you. So what we have in the classification report, the F1 score is there, the precision is there, the recall is there. The root mean square error, this is a metric that is used to evaluate your linear regression models. And our classification report, this is for this, you can generate this when you have a classification problem. So if you have logistic regression, if you've created a logistic regression model or a decision tree model, you will use a classification report, because it's going to show you the different classes that have been and how they have performed within your model. But the root mean square error, this is for the linear regression model. We move to the next question. How do you obtain the optimal number of clusters to use in a k-means model? So the optimal number of clusters, you have the option of plotting the data and trying to see if yourself you can find the number of clusters. However, as your data sets or your data points become very, very, very many, you may find that many points are around a certain area, but that does not mean that they have been clustered together. Those data points may not be similar. So it is not, you may not exactly be able to tell the number of clusters that you have. So randomly is also not a viable option, because that means you're not taking into account that optimal number of clusters. There's an optimal number of clusters that you can create. And if you choose at random, you may just choose maybe one number and a different number, and then another number that you have not chosen is your optimal number of clusters. So you need to have a way that is you need to have a method that is going to determine the optimal number of clusters for you, so that you don't have to go through all this. So you cannot choose your optimal number of clusters randomly because you do not understand the data points. You cannot use using means. Using means, this is also not what you will be after, because you have to calculate, you have to put the clusters together and then calculate the means of those clusters, so that you know if all the data points within a certain cluster are similar or not. And then if they're not, you have to assign them to new different clusters and then calculate the mean again. So this is also not a viable option. We have the using the elbow plot. So this is the correct answer. The elbow plot takes what it does with the elbow plot is you have that function, the WCSS function, that calculates the distance from a data point to a certain centroid. So what happens with this, with the elbow plot, is in the background, it's able to plot the data that you have, and it's able to plot them using very many, the number of clusters that you would want to pass. And then of those many clusters that you have decided to pass, it's going to now tell you which is the optimal number of clusters. So it's going to, for instance, if we say you wanted to plot all the way to 10 clusters, so it's going to plot the data when it has 1 cluster, when it has 2, when it has 3, all the way to 10. And then it's going to look at that data, and now it's going to be able to tell you which is the optimal number of clusters. So with the elbow plot, we realized that how you read that graph. So that graph is usually, what is on the y-axis is the WCSS, that is the distance of the data point from the centroid, and on the x-axis you have the number of clusters. So the line that is going to be plotted on that graph, we said that you can think of it as your arm. And so where your arm branches off to be your elbow, where at that point where you know you can lift and put your arm down at your elbow, that is where your optimal number of clusters is on that plot. So this is the viable option, that is using the elbow plot to tell you the optimal number of clusters, as opposed to choosing them at random or having to plot these clusters yourself, and then you try to decide which is the optimal number of clusters. So that was that. And then we have the last question. What kind of a chart is closest to a decision tree? I would say it is a flow chart, because a flow chart, what it does is you have whatever is the very first variable that has not been split on any variables yet. And then after that, with a flowchart, the idea is if this has satisfied this condition, then go to this side and do this. And if this has satisfied this other condition, then go to this other side and do this. That's very similar to what happens in a decision tree. So a decision has to be made. And once the decision is made, then it's able to decide, once the decision has been made, do this. Once the other decision has been reached, do this. So that is what you have with your flowchart. A tree map, no. A Gantt chart, nope. And a Sankey plot, to be honest, I don't even know what that is, but I know that the correct answer for this is a flow chart. So I hope that quiz was not too difficult. We're going to do a very, very, very slight review of random forest, because we had remained with that. So I have already mentioned that with random forest, it's something very similar to a decision tree, just that with the random forest, you create very many decision trees using random samples of data, so that every data point is going to be represented, as well as with random combinations of your independent variables, so that it's going to be able to gauge, out of all decision trees that have been created, which independent variable seems to be the one that is adding most information to your data. So we're going to do that very, very briefly. So this is where we got to with the other group yesterday. I'm just going to run all the cells. So from SK1. So I'll just have random forest here. Then I will call the data frame so that we can see. So we use the dataset Kyphosis to show this random forest. So with a decision tree, you're just creating one decision tree. However, with a random forest, so in context with this dataset, with this dataset, so kyphosis is a spinal disease. So this data set was to determine, after the corrective spinal surgery has been performed, what is going to, are you going to get kyphosis afterwards or not? So depending on these variables, we want to determine if kyphosis is going to be present or absent. So this was in the medical field. So on top of classifying if someone would have kyphosis or not, they were also interested in how the decision was being made. They will be interested in knowing, is age the larger factor that is going to determine if you'll have kyphosis or not? Is it the number? So number was the number of levels of the spinal cord that were operated on. So is it the number of the levels that is going to determine, is that the larger determinant of if kyphosis is absent or present? And then you have the start, that is what is happening with your random forest. On top of solving your classification problem, you're also interested in knowing how the decisions were made, which independent variable is a larger determinant of what your dependent variable is going to be. So for random forest, we're going to import the library from sklearn.ensemble. So we have something called ensemble algorithms. So ensemble algorithms are algorithms that bring different algorithms together so that your final output is going to be more accurate. So if you want to bring different models together, there's for example, your linear regression is not going to be able to take categorical variables, but your decision trees is going to be able to do that. So you may want to bring the upsides of two models together, and it's going to affect your accuracy. Your accuracy is going to be much better. So ensemble algorithms are algorithms that bring different algorithms together so that the final output is going to be much more accurate. So from sklearn ensemble, we are going to import random forest classifier. Just really done that. So after we have done this, remember the first things we have to do when we have our machine learning is you have your data stored somewhere. So you have to do your feature engineering. You have to pick the variables that are adding information to your data, and then you can know how to pass them to your model. So I'm going to store my independent variables within a variable X. This is going to take age, number, and start, and I store my y, and I store my independent variable within a variable y. So we have done the first bit of the machine learning. We have done our feature engineering. We have picked the data that is important to us. After you have done this, remember you have to split your data into the test set and the train set. So from sklearn, model selection, So model selection, import train test split. So we are now going to split our variables into a test set and a train set, and I'm going to save them within these variables. So the train set for X is going to be stored within X train. The test set is going to be stored there. Then the same for Y. So we have Y train, Y test, and then train test split. X, which is going to be split into X train and Y test. So you have to make sure the order in which you pass the variables to hold the train and the test data are next to each other, because X is going to be split into X train and X test. If you put your Y train here, whatever is going, the X is going to have been split and the test set has been set aside, it's going to be stored within the variable Y train. So when you're passing it to the model, you're going to be passing wrong information. So you have to be very careful about the order in which you pass these variables. So X, Y, and then we have the parameter test size, so that we tell it what percentage of our data you want to use for testing and what percentage you want to use for training. So I'll use a test size of about 30%. So task size is also one of those things that you can mess around with, that is going to give you either better or worse accuracy. So if you have you've created your model, you're evaluating it, you see that you have an accuracy that you're not satisfied with, among the parameters that you can change is the test size. So test size is not set, it's all up to you. And then we have the extra parameter random state. This is just to ensure that the points that are going to be put within your train and your test sets are going to be random enough so that every data point within your data set is going to be represented. So I'll just pass something very simple. So we have now split our data. So we now go to moving this data to the model. So we have already imported our model, but we need to create, our algorithm. So we need to create an instance of it. I can call this, just call it random forest. So you create an instance of it. So random forest classifier, simple as that. Then after you have created an instance of your algorithm, remember you now have to call the fit function first. So the fit function in the background for this random forest, what it's going to be doing is it's going to be creating those very many decision trees with the random data as well as with the random combination of your variables. That is what happens when you call the function fit for this random forest classifier. So we have the random forest, and so we call the fit. And then we are fitting the data that is within our X train and our Y train. So it has, after it is giving us this, then it's telling us it has drawn all those trees and it has already gotten, it has already calculated the, okay, it has already created those trees. That's just it for this. So it has, with fit, it has created the trees. And then now you'd want to make some predictions from the model that you have learned so that you can compare it against values that you already have within your model, so that you're able to tell if you, the accuracy of your model. And the accuracy of your model is going to be able to tell you how much can I trust these predictions that have come from this model. So we now predict some values. So I will store these values within a variable predictions. And so we have, so for predictions, you use the function predict. It's very simple. And we're going to predict, we want predictions from what is within our X test, so that we're going to compare those predictions against what is within Y test, which is data that is actually within our data set. And that is going to help us assess the accuracy of the model that we have created. So, yeah, so we have predict, and we're predicting the values that are within the X test. So we have gotten our predictions. We can look at what they look like. So predictions, so it's predicting for you if it's present or absent, very similar to what we did with the decision tree. However, now let's look at the classification report, or the classification report, so that we're able to see the accuracy and compare it with the accuracy of the decision tree, so that you're able to know which of them is performing better. So from sklearn, dot metrics, we will import the classification report as well as the confusion matrix. So to look at the classification report, because this will give us a bit more information at first. So again, the order in when you're evaluating your model, that is, you're using functions from the metrics module. The functions that you're going to use, you have to be careful about the order in which you pass the data. So the order in which you pass the data to these metrics functions is you have to ensure you pass the true values first, that is the values that are actually within the data set, and then you pass the predicted values. So for me, the values that were actually within the data set are stored within whitetest, and the predictions that have been made have been stored within the variable predictions. So we can see from our classification report, so this is helps to answer one of the questions we had in the quiz. We can see precision, we can see recall, we can see F1 score. So these are the metrics that you can get from the classification report, and we can also see the accuracy. So this translates to 76% accurate. And when we had our decision tree, so it still had an accuracy of 76. However, generally, you should get better accuracy with your decision tree. This was a very small data set and it was very clean. So we already kind of knew what we were after. However, with a data set, a real world data set, a random forest should perform better, because what it's giving you, the result it's giving you is an aggregate of very many decisions. It's the decision that has been made the most number of times, unlike with a decision tree, which is just one decision. So generally, your random forest should give you better accuracy. This was just a very small data set, but that is all you need to know about random forests. So if there isn't any questions, I think we can move on to the next thing. Okay, I will assume there is no questions with that. So we are now going to move into something else. So let me get to there. Okay, so I hope you can see this screen. Sorry. So we now move into natural language processing. So natural language processing, this is the processing of natural language. So natural language is the language that we use to write, the words that we use to communicate when you're talking to somebody else. So you can hear that within this natural language, this is your speech, what you type, the text that you send out. So within this natural language, the data that you send out, whatever you type, for instance, if you were sending a text to somebody, if you were maybe telling them that the year you were born in is whatever year you were born in, your name is whatever and what have you and what have you, this data has not been structured. It's, if you were to put it in an Excel sheet, it will not make any sense. You cannot be able to perform any analysis on it. This is because, for example, if you say, I was born in the year 1990, so within that, we have a parameter, we have some string values, that is my, I was born in the year, and then the value of the year is now either, so it can be, that is going to be a time series, but you can opt to save it as an integer. Yeah, you can opt to save it as an integer value. So we need to find a way to process this this unstructured data, such that we're able to access various components within the natural language, and we can perform some analysis. And on top of that, if you want, you can be able to store this data in a database. So natural language processing is about breaking down data that has not been structured into structured data. So you take in, for instance, the text that you have sent to somebody. You're able to break that text down into different portions that you can access, and then you can now perform your analysis on these portions that you have been able to break down your text into. So that is what we're going to be doing with natural language processing. We have previously been working with structured data. So structured data is that data, it has a defined data schema. If you go to Excel, your data has been put in columns. Each column is holding a specific kind of data, and it's one observation. It's if it's, for instance, if you had that sentence, I was born in the year 1990, I was born would probably have been stored in a column, maybe sentence, and then 1990 is stored in a column year. So that is structured data. However, with unstructured data, you have your text values in there, your numbers, your punctuation marks, you have everything in there. So with this, what we're going to be trying to do is breaking down that that whatever is in that natural language. For instance, if it's text, you're able to break down that text into smaller you're able to break it down in such a way that you're able to access those individual elements within that natural language, as well as perform some analysis on it. So NLP allows us to analyze data that is not structured, that is data that is within text files, audio files, yeah. So this is the very basic flow of how it usually works. So I'm going to take you through this before we go to the actual coding of it, so that when we get to coding, it's a bit simpler. So what happens is you have your data stored within a text. So this is your text. So the first thing that happens with NLP is you have to tokenize your text. So tokenization is, let me try and make this. So tokenization is separating pieces of texts into smaller chunks called tokens. And these tokens are the building block of NLP. So the very first thing you have to do when you receive your data that you're trying to process, you have to break it down into tokens so that you'll now be able to do some analysis or whatever you want to do with that data. So the very first thing you have to do is tokenization. And once we get into the code, we're going to see that this is something that is going to be done for you using a certain library, I should have mentioned. So for natural language processing, just as with data analysis, we know we use the libraries NumPy and Pandas. For visualization, we use the libraries, we have Seaborn, you can use Plotly or Matplotlib. So for natural language processing, there is also a library that is very useful for it. So there are also several libraries. It's dependent on what you'd find easier for you to use. So for this class, I'm going to teach you NLTK. So that is the natural language NLTK. That is natural language. I think it's natural language kit. Yeah, it should be the natural language kit. So that is the kit that has everything you need to process natural language. But there is also another library called Spacy. At your own time, you can go find out about it. You might find that it may be easier than NLTK, or NLTK may be easier than Spacy. They all do the same thing, so it's dependent on you and the library that you're going to find simpler. So someone has put something in the chat. If you would kindly just say it out loud, because my chat is not opening for one reason or the other. You can just say what you wanted to say out loud, please. Okay, so just feel free to stop me at any time if you have anything to say. So with tokenization, you don't have to worry about this whole tokenization. It's going to be done for you. So it's going to be done for you from NLTK. Yes, so NLTK, it stands for the Natural Language Toolkit. So it contains all the things that you will need to perform your natural language processing, including the things you need to do this tokenization. So within tokenization, there are also several kinds of token. So whatever is doing this tokenization for you is called a tokenizer. So there are several kinds of tokenizers. Again, you don't have to worry about it. You don't have to write any code for it. You just need to import it and it's going to do the tokenization for you. So you just need to know the library or the module that is going to do this for you. You just import it and it's going to do everything for you. You don't have to worry about that. So after the text has been tokenized, the text has been broken down into several smaller bits that can now be accessed. We now move to pre-processing text. So within pre-processing text, this is something very similar to pre-processing your data that you had before. For instance, with the Kyphosis dataset, you'd want maybe to do some data cleaning. So this is pre-processing your data so that you send it to a model. So that is for supervised learning and with structured data. However, here when you have your unstructured data, you'd be pre-processing the text that you have tokenized. And so the idea of pre-processing is removing all the information that you do not need within this text so that you remain with the information that is relevant to you. So within pre-processing text, we can see we have removing stop words and then stemming and lemmatization. So removing stop words are words that are very common in English, and within a sentence, because we are processing text, within a sentence, they do not give any more information to that sentence, but for the sentence to make sense, they need to be there. So stop words include words like there, and this, have, had. So these are words that for the sentence to make grammatical sense, they need to be there. However, they do not provide any more information to the sentence. So you may opt to, especially if you have very, very, very many words, you may opt to remove the stop words so that you remain with the words that are adding meaning to your data. So the first thing you do is removing the stop words. Again, NLTK is going to be able to sort you with this. And also if you opt to use spaCy or whatever other library that assists with natural language processing, it should probably come with a way for you to remove stop words. So again, you don't have to worry much about that. The library is going to take care of it. And then after you have removed the stop words, we move to stemming and lemmatization. So stemming and lemmatization, these are methods that are going to help you to group words together. For instance, you may have a very long bit of text about maybe someone who was taking a trip around the world. So you may find that the word fly is going to be very common within that text. However, the word fly is going to have very many variations, maybe depending on tense. So you can have fly, you can have flying, you can have flown, you can have flew. So you may want to group all these words together so that also you're not working with so much data. So to group those words together, that the words that refer to the same thing, that is the fly, the flew, flown, they all refer to the verb fly. If you saw any of those words, the first thing that clicks in your head is fly. You already understood the information that it's sending out. So you do not need to have those very many variations of a single word. So to group words that have the same meaning together, that is called stemming, and it's actually called lexicon normalization. And so the forms of lexicon normalization that you can have are stemming and lemmatization. So we are going to see within code what this means. So after you have pre-processed your text, you have removed all the noise from it. So anything that is not adding information to your data, we call it noise. So you have removed the stop words, you have removed a form of noise, you have grouped all the words that mean basically the same thing together. So you have also removed some noise, that is the words that have some sort of variations that would have been treated as different words, they have now been put together because they are trying to pass on the same information. So after you have done your pre-processing, you can stop at this point if you are not interested in building a model from your data. You can stop at this point. At this point, you'll be able to perform some EDA. I'm going to show you. So at this point, you'll be able to form some EDA and you'll be able to get the data you want. However, if you're now interested in creating a model from your data, for instance, you may have several text documents and you'd want to classify them together. You'd want to group them together. So you can you want to classify them. For instance, maybe you have something that belongs to news, you have something else that has information about politics, you have something else that has information about entertainment. So you want to classify these documents into you want to classify them. You want to put things that are together in one place and things that are also together in a different place. So if you're interested in doing something like that, you would now be you'd want to now create a model that is going to classify these documents for you. So with that, we move into feature engineering. So within feature engineering, remember that we have said most of the models that we have, they do not accept categorical variables or string variables for that matter. They need to be given numbers. So we need to find a way to map the words that we have to numbers so that we're able to create a model from it. Again, you don't have to worry about that, and it's not you don't have to worry about that. The library is going to be able to take care of that. So you have several ways that you can opt to create those numbers that are going to map, to create the numbers that are going to be mapped to your words. So you can have a bag of words. You can use TF-IDF. This is term frequency inverse document frequency. At your own time, you can go look at what exactly it means. But again, this is just a function that you can call and it's going to do whatever you want for you. So if you're more interested in just the output, you don't have to worry much about it. But if you're interested in it, you can always go find out what TF-IDF is about. You can also have a word embedding. So at this point, it's going to map your words to a certain number. And then now this number is the number that is representing said letters are what are going to be taken to the model. So for instance, if you wanted to classify your text documents, you'd now have an algorithm, a classification algorithm. So that is where your model will be built, and then you can evaluate your model. So I think we can now move into the actual code of it. So just a brief overview. You have your text. The very first thing you have to do is tokenize it. So tokenizing is breaking your large text into smaller chunks, and these smaller chunks are called tokens. And these tokens are the building block of NLP, something very similar to how arrays are the building blocks of NumPy. The very first thing you have to do is understand the working of an array before you can understand NumPy. So for this, you have to understand the idea of tokenization before you can move into something else. So the first thing, you have your text data, you tokenize it, that is breaking it into smaller chunks, and it's also going to help you to be able to access elements within that text. After you have broken the text into chunks, you move to pre-processing the text. So this is about removing all the information that is not important to you. So within pre-processing, among the things you can do within this is removing stop words. So we have said stop words are words that do not add information to your data. They're only there because they help the sentence to make grammatical sense. However, for us, we may opt to remove those stop words, because if you have a lot of text and you're trying to do some analysis in it, you just remove what you don't need and remain with what you need. So after you have removed your stop words, we have seen you can now move to stemming and lemmatization. So this is about bringing words together, words that mean basically the same thing. You bring them together so that you do not have very many words that all mean the same thing. They're all giving you the same information, yet you have so much, very many occurrences of it. So also, as you're passing information to your model, try to make sure that each data point is as unique as possible so that your accuracy is going to be better. So with stemming and lemmatization, we're just trying to bring the words that mean the same thing together so that we do not have so many words. After, at this point, we have said you can opt to stop here. If you're not planning to build a model from this, you can opt to stop here. At this point, you will be allowed to do some EDA. You can be able to see, for instance, if you wanted to perform some sentiment analysis, at this point, you can be able to see the words that pop out the most. So that's going to tell you the word that has appeared the most number of times within your document, the words that have the most weight within your document. However, if you're interested in building a model from the text that you have created, you now have to find a way to map the words to numbers, because models do not accept, most models do not accept categorical variables or string values of any kind. They need to be numbers. So within feature engineering, you would choose a module, a library, an algorithm that will assist you to map the words to certain numbers. And then you can now pass those numbers to your model. Again, depending on whatever you're trying to do, it's going to determine the model or the algorithm that you're going to use. So after you have you've chosen your algorithm, you have built your model, and then you evaluate your model. So we now moved to the coding bit of it. So I'm going to create a new notebook. And I'm going to call it NLP. So we are going to, the first thing for you guys that you have to do, so we have said that the library that is going to assist us to perform this is the Natural Language Toolkit library. So we need to import it. For me, I already have, but for you, I know you do not have it. So just type this and you should, it should be able to download it for you. So so Eric, you're a bit better at importing these things inline. Inline is this, right? It's the exclamation mark and then pip install.
You can actually do it without the exclamation mark. So just pip install NTK.
So just pip install.
Yeah.
Okay. So for you guys, kindly run this. For me, I already have this installed, so I'm just going to import it. But please run this piece of code and then let us know if there's any errors so that we don't leave anyone behind. So after you have installed it using pip install NLTK, you can just come to a different cell and then now you can import it. So with this kind of importing libraries, installing libraries, this library has only been installed for this notebook. So if you want to use NLTK for a different notebook, you can now install the library on your Anaconda distribution. So that will be using at the Anaconda prompt, or you have to do this at the beginning of that notebook again. So note that this has not imported it into your Anaconda distribution. This has just imported this library for this notebook. So no complaints. So I'm hoping everyone has been able to install it. So first of all, we're going to show this on a very simple piece of text so that you're able to understand it, and then we can be able to do it on a larger scale. So I'm going to create. Yes.
It's asking to install to restart the kernel.
Yeah, it's okay. You can just do it.
Okay, thanks.
Okay. So we're going to create some very simple text here. Rather, let me see if I can share the text that I have with you on chat so that I don't have to write too much of it. So just copy that bit of that text exactly as it is. We can save it within a variable text. This is what we are going to show. This is what we're going to use to show the capabilities of the NLTK. And then if we have time, we can do it on a data set. So yes, that is. So this is the text that we're going to be performing our natural language processing on. So we have said that the first thing you have to do once you have gotten your text is tokenizing. So we are going now to access the modules within NLTK that are going to enable us to tokenize this. So we have from NLTK, at least I hope it's tokenize. So tokenize import. So we have some few tokenizers here. We have sentence tokenize, and we have word tokenize. So these are types of tokenizers that are within the toolkit NLTK, within the toolkit of natural language processing. So just to do that. So now we are going to tokenize this. We're going to tokenize this text. That is, we're going to be able to break it down into. We're going to be able to break it down into smaller chunks. So this text consists of some 4 statements. We have, hello, Mr. Smith. How are you doing today? We have, the weather is great and the city is awesome. The sky is pinkish blue and you shouldn't eat cardboard. So we now want to be able to break this into smaller chunks so that we're able to perform our analysis on it. So I'm going to be storing whatever the tokenized values within a variable. So this is the variable that is going to hold that. And I'm going to call this, tokenized. I can call this sentence. Just leave it at sent. So equals to. So the first tokenizer I'm going to show you is the sentence tokenizer. So what sentence tokenizer does for you is it's going to be able to take in your text and break it into the sentences that are in there. So we can have, then we're going to tokenize whatever is here. And then we can print the results so that we can see what has happened. So it has taken in this text. You can now see we have some square brackets around our information. So after it does the tokenization, it stores the values within a list. So the data structure that you're working with now is a list. And what you can see within this, we know that the values within a list are separated by commas. So you can look at your commas so that you can know the kind of different elements you have. And so the first comma is here, and we can see that means our first statement is, hello, Mr. Smith, how are you doing today? And that was our first sentence. And then we have what comes after that first comma. We have, the weather is great and the city is awesome. So it is also able, you can see that that is a whole sentence that has been set aside. So with sentence tokenization, you're breaking down your large text into the sentences, the number of sentences that are there. And those sentences are going to be stored within a list kind of data structure. So you have broken them down into sentences. However, you can also break them down into words. So we will do that and say, so this is going to use our word tokenize, and we want to do that. And then we print the results. And so you can now see it has now been able to break down our sentences, or rather our whole text, into the different words that are in there. So I should have shown you this. So for instance, now at this point, after you have tokenized, now this is behaving like a list. You can be able to access the individual values within this list. For instance, if you wanted to access the first sentence within this list, you just pass the index position 0, and you can see that it's now you're able to access different parts of your large text that you had. You have tokenized it, you have broken it down into smaller chunks, and you can now be able to access the chunks that it has been broken down into. So that is if you wanted to access the first sentence, you just pass the index position and you're going to get what you want. The same thing goes for the words. So if I pass the index position 0, it returns for me the first word within the list. So at this point, you can now see what you were not able to access because it was just a whole chunk of text. You can now be able to access some individual elements within that text after you have tokenized it. So after tokenization, we have seen that the next step is now pre-processing of the text. So you have broken down the text into much smaller units that you can now work with. So you now want to remove all the noise that is within your text. You want to remove anything within the text that is not making any sense. So the first thing we're going to do is so within this, the output that we can see that, so hello, Mr. Smith, how are you doing today? These two statements were separated using a comma. And you can see that within our list, after we have tokenized our text, we can see that the punctuation marks as well have been treated as words. Punctuation marks are not, they do not add any information to your data. So you may also want to remove punctuation marks. So to do this, you can use a different tokenizer. There's a different tokenizer that is able to, it's able to understand a punctuation mark, and it's also able to understand that once it encounters that punctuation mark, it's supposed to drop it from the resulting list. So we're going to use that tokenizer, and it's, what is it? Let me look for it. Here it is. So this is the other kind of tokenizer. It's still from the NLTK toolkit. So from nltk.tokenize to tell it what module you're trying to read from. So we had imported sentence tokenizer and word tokenizer, but now we are going to import this regex tokenizer. So regex is regular expressions. And so using some certain patterns, using some regular expressions, this tokenizer is now able to drop your punctuation marks so that the resultant list that you're going to have is going to be a list that just contains words. So you can import that. So it's regexp tokenizer, just import that. And then we are going to do the same tokenizing, just that we are going to see a list that does not have punctuation marks. We have started now to remove the noise within our data. So I will draw this, just call it tokenized. And so this requires me to have so regex tokenizer. This takes something else a bit extra. Okay, so there's this thing we have to write here. Okay, so I had forgotten. So within this regular expression, what happens with this tokenizer is you create a certain pattern, and then you now apply that pattern to your data. So the pattern that we are creating here, this is a pattern that is going to remove punctuation marks for you. You don't have to worry much about what the pattern means. You just need to know what it's doing for you. So you can just type it. So tokenizer, this is creating an instance of the tokenizer, as well as giving it the pattern that it's supposed to be looking for in your data. So with the regexp tokenizer, it looks for a certain pattern, and then it which returns for you the values that have satisfied that pattern. So this pattern is going to remove punctuation marks within your data. So after you have done that, so tokenizer, you have set it, and then now tokenizer.tokenize. What are you trying to tokenize? You're trying to tokenize your text. So I will change this to.
Sorry, excuse me.
Yes.
It's giving me an error that I need to download the NTLK.
Yes. So it's telling you to. I'm assuming, is it an error something close to? Okay. So is it telling you have to download this, something like this?
Yes.
So just there's that bit of text that it's told you import NLTK download. Just copy paste that NLTK download the way it is, put it in a cell, run it, and you should be fine. And then run that other cell that was giving an error again. It should be fine now.
Okay, thank you.
Okay, so the same thing. So just you can copy paste that nltk.download punkt. Just do copy paste it the way it is, put it in a cell, run it, and then after you have run that cell, so you're going to have copied it here, run this cell, and then the cell that was giving you an error, run it again after you have run this, and you should be fine. So I hope that sorts you guys. So we now look at this data that has some noise removed from it, so tokenized. And you can now see there is a difference between the output we have here and the output we have here. The output we have with our word tokenizer, you can see we have a full stop that has been stored here. We have a comma that has been stored here, a full stop here. However, when we have used this regexp tokenizer, you can see we do not have punctuation marks. So we have started to remove noise from our data. So now we are moving well. So you have now created, you have tokenized your words, and the resultant list does not have punctuation marks. So now the next step is to remove the stop words. And I think I will demonstrate something for you to see why you would want to remove your stop words. So you can look at the distribution of the words within the text that you have, the tokenized text that you have created. Okay. Someone needs some catching up to do, so no worries about that. So this is just, so what we're going to be trying to do now is look at the distribution of these words so that I can show you stop words occur a lot. So there are a lot of noise within your data. So I just want to show you something that is going to show you why you'd want to remove your stop words from your data. So to remove the stop words, so you don't have to worry about this plot that I'm about to draw. You don't have to worry about this bit of code that I'm about to write now. I just want to show you the distribution of these words so that you can understand why it's important for you to remove the stop words within your data. So from NLTK probability, we import frequency distribution. So you can do that. And then we will store. So we're going to do a simple plot. So I also have to import matplotlib. So I will store these within frequency. So we have tokenized can see that. And then we can very simply plot this. So you can see that this is just a very brief distribution of the words as they have occurred in the list that I have, that contains the words I have tokenized. And so you can see the ones that have the highest occurrence, we have the word is that has occurred 3 times, and is not giving us any information. So is one of the stop words that we have. So you can see it has 3 occurrences and it's not adding information to our data. So we would want to drop it. So along this, you can now see the number of times words have appeared within the text that you have. This is good for this because it's very small text, but if you have a lot of text, you probably won't be able, or it won't all be able to fit here. So that's why we have opted to use very small text for now. So you can see that is has occurred 3 times, yet it's not adding any information to our data. So we would want to remove the stop words. So to remove the stop words, we're still going to use something within NLTK. So we have from NLTK, is it stop words? So we can have that one, yeah. So from NLTK.corpus import stop words. Okay. It doesn't have the underscore. So there are some defined stop words. There are stop words that have already been defined for you, so that you don't have to start defining what stop words you want to remove from the data set. So we can have a look at these stop words. So these are the stop words that are within. I think you will get an error with this. So you might get an error. If you get an error and it's going to tell you to download stop words, just copy paste it, put it in a cell, run it, and then run the import statement again. So this is the stop words that are within NLTK. These are the ones that have already been defined for you. So you see we have words such as this, to, him, because, shan or shan't, doesn't do. These are words that for a sentence to make grammatical sense, they need to be there, but as you're trying to do your analysis, they have no information. They add no information whatsoever to your data. So we want to remove stop words, and so we're going to create a very simple function for this. And something else to notice about stop words do not, none of them have capital letters. So if your word within your text data is starting with a capital letter, it's not going to be treated as a stop word because Python is case sensitive. So for instance, a there that starts with a capital T is different from a there that starts with a small t. So among the things we want to do first before we can remove our stop words, we have to convert our text, all of it, into lowercase, so that if the function we're going to write encounters a stop word, it's going to be able to recognize it because it's also going to be starting with a small letter. So I'm first going to write something that is going to a bit of code that is going to convert my my text into so like Mr. and Smith, they have capital letters at the beginning. So I'm going to write some code that is going to convert everything into small letters. So I will save that within a variable, so lowered case. And I'm going to what I'll be trying to map is yeah. So this is a very, very, very simple function. So let me try explain what it's going to do. So what this function is going to do is, so this is a lambda function. A lambda function is a function that has not been, it's an anonymous function because it hasn't been given a name. So it's going to take in the argument x. So x is going to be one of the words that we want to take in. So it's going to take an argument x, and then it's going to perform this. So dot lower, what it does is it takes all the text that you have given it, and it's going to convert all the words into, rather all the letters into small letters. And then we also have to give where are we picking these words from. So they're being picked from the list tokenized. So what is happening is it's going to pick a word from tokenized and store it within x. Then it's going to take x and convert everything to lowercase. So map basically means that we want to do this for each and every element that is within tokenized. And the function map does not usually give you a readable output. So for you to read the output that has been that has come from this, you have to put it within a list. Okay, sour. So okay, where exactly are you, so that we can catch up from there? So I think with this specific, for this specifically, because it has a lot of, you'd be more interested in the output as opposed to the things that you're doing in here. I'm going to write the code, and then I will try and I will send this notebook to you guys immediately after this, so that if there's any bit of code you did not get or understand, you can run it at your own time and try and find out what it does. So where exactly are you, Abraham, so that we can, you can catch up? Okay, but let me start by putting this here. So that is the code that is going to change our words to lowercase. Oh, okay. So so let me just put this in quick succession so that you just run them one behind the other. So there's that. You don't have to worry much about this. I will give you the notebook for that. And then we are now here. So just run the regexp tokenizer so that you're able to be working with the same data that we are working with. So this is going to be the So this is going to be the code that is going to convert our words, all of them, into smaller, into lowercase. So we can just look at the output after this. So you can now see Mr. for Mr. Smith is in small letters, S is in small letters. Everything we can now see here is in small letters. So we can now move to writing the code that is now going to remove our stop words. This is also some bit of code. I think it will be easier for me to just copy paste it so that we don't spend much time here. I've also sent this bit of code to the chat. So basically what is happening here is we have created an empty list. So this empty list is going to now contain our new words that do not have stop words. So we have created an empty list here. And then we have said for, okay, so we have to change a few things here. So for word in lowered case, so lowered case is that list that we have created that has all our words in small letters. So what it's going to do, so the for loop, what it does is it picks each and every element within your list. So for each and every word that is within the list lowered case, so for each and every one of those words, if word not in stop words, so at this point we have not even declared what stop words are. So you have to do this, stop words equals to set stop words stop words dot words English. So with this, we're just storing those stop words within a variable so that we are able to pass that that variable here, so that all those stop words have been put together in one place. So our stop words that are the ones that have already been defined within NLTK, we have now stored them within our own variable stop words. So now we come back here. So if the word that is within the list that has the text being in lowercase, if that word is not within stop words, so that means the word is not a stop word, then add that word to the filtered text, that is the empty list that we created. So the empty list, the empty list that we created, by the end of this is going to contain all the words within our list that are not stop words because of this one bit of code. So if the word within the list is not in stop words, so stop words are the stop words that have already been defined for you within NLTK. So if the word that we have picked from our list is not within these stop words, then that means it's not a stop word. Then put it then add it to this empty list that we had created. So we're now going to have a list that is going to contain the words that have no stop words. We are now removing noise from our data. So the tokenized, let me not call it tokenized sentence. So I can call this, tokenized sentence is well enough. So tokenized sentence, but this is going to show tokenized. And then we have the filtered sentence that will show what is here. So we can see that within our tokenized sentence, we have hello, Mr. being capital M. This is the sentence when we got it from our tokenizer. So with our filtered sentence, this is when we have removed our stop words. You can see we do not have how, we do not have are, we do not have you. It has removed all the words that are within the stop words that have already been defined. So we now have remained with information that is very specific. It's information that is giving us it's data that is giving us some information. So we have removed our stop words. So with this small data set, we do not have to put our words that mean the same thing together because we do not have such words. However, I'm going to demonstrate this. So so this is so in the event that one has a lot of text, some words may be repeated in the sense that different variations of the word are present in the text. That is, for instance, considering the text, one may have the words fly, flying, flew, flown. So in the event that you may wish to bundle up this all these words that have the same meaning together, it will make looking at your data a whole lot easier. And this is called lexicon normalization, and there are several ways to do it. So the several ways to do it, we have stemming. We saw from the picture, we had stemming and lemmatization. So this stemming is done by the quote stemmer, and then lemmatization is done by WordNet lemmatizer. So I just want to show you the difference between those two things. So if we import the stemmer, so again, we have said that these are just trying to bundle up words that mean the same thing together. So if we had the words fly, flying, and flew, if you were to stem these words, that is, you're trying, so with stemming, it tries to look at the first few characters that are similar in all the words so that you are able to, whatever is beginning with the same characters, go to put together. So for instance, if you were to stem the word fly, this becomes the stem of the word. Flying, you can see it also. So flying and fly would be grouped together because they begin with the same characters. That means they are probably the same word, but flew remains as flew. But you would like this flew to reflect, because it's still about flying, you would like it to reflect as well. You'd like it to reflect with the other values that you have gotten. So stemming is not, so you have stemming and lemmatization. Stemming does not give you exactly what you're after. So most people tend to use the lemmatization. So with lemmatization, you import whatever. So if we try to look at the base of the word flew, you can see it tells us fly. So so with lemmatization, with this library, WordNet Lemmatizer, even if the word does not start with the same letters, it's still able to understand that this is just a variation of a certain word. So if we had the words fly and flew within our data set, they would all be grouped together because they basically refer to the same thing. So within the data that we are using, we do not need this. So this is just to show you. I'll also try put this within the notebook before I send it to you. So after that, you have done your pre-processing of your data. So if you do not mean to build a model from that data, at this point, you will now be able to perform some EDA. And I'm going to show you that using something really cool. We're going to create a word cloud. So again, you are going to have to import this. So I hope pip has it. So pip install, let me just look for it. So pip install word cloud. So okay, it's just word cloud. So for you guys on your end, for me it's already installed, so you guys have to install it. This is the code that is going to help you install that word cloud. So just run that. Let's write the code, and then I'm going to send it to you just after this, no worries. So from word cloud, we are importing word. So word cloud, the library word cloud has also its own set of stop words, just as NLTK has its own set of stop words. So as we're drawing the word cloud, we're just going to use the stop words that are within the word cloud library. So there is a certain kind of input that this word cloud expects. So for instance, it does not, it expects the values to be given as a string and not as a list. So we have to convert our list to a string, and that is done very simply by using the function join. So what we're going to be joining for us is what is within so we have what is within our array filter, so we are going to convert this list that contains our words without any stop words. We're going to convert it to a string. So that is done very simply using the function join. Corpus.replace, you don't have to worry much about this as well. So how you draw this, the word cloud, so you have so we have word cloud. So this is creating an instance of the word cloud. So word cloud, the stop words that are supposed to be considered stop words, we have created our own stop words. That is what has been stored here. Can pass the background color, the width you want, as well as the height. And what it's to generate within this word cloud is the values that have been stored within corpus. So I'll send this information to you just right now. I want you to see the output first. So this is the output of our word cloud. So what a word cloud, this is now your EDA. Because you're working with text information, you cannot do something like a value counts. Like for instance, we had our data frames where you could do data frame.value counts so that you're able to see the kind of values that are within a column and how many times it has occurred. Because you're working with text information, you're not in a position to do that. However, using this word cloud, you can be able to get something from it. So this word cloud, what it's showing you is the words that have come out, the words that have a lot of weight within your text. For instance, we know that hello has a lot of text because it's in very huge letters. We have Smith has a lot of weight within the text that we have given it because it is in big letters. So this is how you would do an EDA for for text data. I think I have something that will show this a bit better somewhere. Can you guys see this screen? I hope you can. So this is just something very simple. So this guy performed some sentiment analysis on data from Twitter. So he picked in some data, and then the data had been tagged as if it's a positive or a negative. So he took in the data, and what he was able to do, so he was able to segment what had been given as positive feedback in one place, and he put what was given as negative feedback in a different variable. So he was able to draw a word cloud. So this is the word cloud that he was able to draw with what had been tagged as positive news. So you can already see these the words that are really jumping out. So for instance, we have last night. We can see we have Trump, we have candidate. These are the words that have come out the most in the text that was tagged as positive. And then for the text that was tagged as negative, there's also the words that really came out in it. We can see Trump, we can see debate. So maybe anytime people are talking about a debate that was, they were saying it with a negative tone. Anytime they were talking about Trump, anytime they talk about Fox News, last night, Chris Wallace, Jeb Bush. So this, the word cloud helps you to do some EDA. You're able to see the words that have popped out the most, the words that have the most weight within your text. So this is because you do not have the value counts. This is not structured data. So for you to be able to do some EDA, you can draw a word cloud so that you're able to see the distribution of the words that are within your text. So that is how you draw a word cloud. So by the time you get here, if you do not intend to build a model out of this, you've done something. So this data, by the fact that you can access it, for instance, if you want to access this word, you just pass the name of the list with the index position of the word you want to access. With that, you can be able to store these words within a different variable, and then you can put that variable to a data frame and store that data within a data set. So at this point, you have been able to get your unstructured data. And now by the fact that you have tokenized it, you can be able to access those small chunks of the text. You can now be able to probably save it in a data set, perform analysis, or whatever you want to do with it. So at this point, you can opt to leave it here. That is if you do not intend to build a model from it. However, we are now, for instance, so that I can show you how you can build a model from this, we are going to show something very simple on sentiment analysis. So it's going to be, sentiment analysis. I'm going to show you on a very simple data set. However, I can see that time has moved. Eric.
Yes.
This session is supposed to end at 1:15, right?
At 1:15, we could probably push to around 1:20, 1:25, and then maybe pick it up after lunch to complete what's left.
Okay, so there's a data set that where is it? There's this data set, Control C. So go to that link. I have sent it on the chat. So when you get to that link, just scroll chini kidogo. There is where your data is going to be. So there's a train.tsv. After you have selected it, just click on download so that you can download it. And then because it's zipped, you have to make sure that you extract that information, and you can extract it to the working directory that you're in, so that when we're reading it in, we do not have to provide a file path. So just get to that link I've given you, train.tsv. Just scroll chini kidogo, train.tsv, make sure it's what it's selected, and then download it. And it's zipped, so make sure you extract that file, and then you can put it within your working directory. So I'm hoping you have been able to get that data. So make sure you have uploaded it to your working directory. So after you when you want to import it, this is a TSV. This is a tab separated file. So we have to provide, you can see this extra parameter, we have to provide the separator, because read CSV knows that it's going to be reading in a file that has been separated using commas. However, it can also read in files that have been separated by something else, just that you have to specify what that separator is. So for us, because what is separating our values is a tab, this is what denotes a space or a tab in Python. So we have said reading a CSV file, it expects to find a file that is comma separated. However, it can still read in a file that has been separated by something else. You just need to provide the separator. So TSV is a tab separated file. So we have provided our separator as tab. So we can look at what is within here. So we have some few phrases, the phrase ID, sentence ID, some phrases, and then the sentiment that has been attached to that phrase. So you may be interested in creating a model that is going to be able to predict for you the kind of sentiment based on the phrase that has been provided. So at this point, will be some sentiment analysis. However, what you're trying to analyze is text. So you have to find a way for you to be able to get this text, be able to access it, so that you're able to do this analysis on it. Because you have to be able to find a way to get that text and perform that analysis on it. So at this point, we are now going to start doing the very few things that we had seen at the beginning. So we had seen we have to tokenize. The first thing you have to do is to tokenize, and we have seen the different kinds of tokenizers. So just the very few steps that we had done at the beginning, I'm going to do them here for this specific column phrase. So we had this much better tokenizer. So it has been stored within tokenizer. I just need to call it. So I will call this, so tokenized data equals to tokenizer. So this tokenizer that I'm using for this data is the one that is able to remove the punctuation marks from your data. So tokenizer, and what it's tokenizing would be what is within okay. So as we were saying, the tokenizer only accepts, you can see it's telling us that it accepts either a string or byte-like object. So at this point, our phrase, our data that is under the column phrase has been stored under an object data type. So we need to convert that object data type to a string so that we're able to pass it to tokenize. So to do that, Okay, so I think I can show you from here. And then when we come back from, I'll send this to you over the lunch break so that you can be able to catch up by the time we'll be going to finish. So this is what is going to, this is just a process to convert our object data type data into a string that the tokenizer is going to be able to accept. So here what I did was I selected that phrase, and then as I was running this code a bit earlier, I noticed that this data set has 15,600 entries. So it told me that that is too much data. So I decided to work with the first 1,000 lines of data. So I picked the first 1,000 lines of data, and then I converted that that information to a list. So this is a function that is it's native to Python. So what this does is it converts whatever data structure that you have, it converts it to a list. So you can see we have our list here because you can see it is surrounded by the square brackets. And then we still have to convert our list to a string so that it's able to be accepted by our tokenizer. So I just created a very simple function and I called it list to string. So it takes in a certain S, which is a certain list. Then here we've created an empty string. And so what we're going to be doing is we're going to join that empty string to the list that has been provided in here. So what this join does is what is able to convert your list items into a string, because it's basically does that. It joins the different elements in that list. So at this point, this is just a function. So for you to be able to see the output, this is the output. So this was when we converted it to a list. You can see it has square brackets around it. Then when we convert it to string, it now becomes, it has the quotation marks around it. So quotation marks are what tell us that we are working with a string. So as you can see, we had to convert the data in that column to a string because the tokenizer we wanted to use only accepts string inputs. So at this point, you can now pass the string from the data to the tokenizer, and you can now see it's able to do the tokenizing for you. You can now be able to access this individual words by passing the index position of the word that you want to get. So this was again just a frequency distribution to show you. So for this bit of data, we can see that the words that have occurred the most number of times are there, of, are, and, s, to, is. These are all stop words. So the very first thing you'd want to do is to remove the stop words. So to remove the stop words, the very first thing we did was convert all our words into small letters, because stop words have been defined as small letters. So if it encounters a word that starts with a capital letter, yet it is a stop word, it won't be able to recognize it because Python is case sensitive. Something that starts with a small letter, the same word that starts with a small letter and a capital letter, they mean very different things. So we have had to convert the words that are within our list to lowercase using this very simple function. And then after we have converted them to lowercase, we have removed the stop words so that we can remove the there, of, are, and that is going to remove our stop words. So after we remove our stop words for this, this is before the stop words were removed. We have a series of escapades demonstrating the adage that, but once we have removed the stop words, you can see the words we have now are series, escapades, demonstrating, adage. These are words that are giving us some more information about what we are trying to do. So with this, you can also opt to look at the word cloud, but this not so much, because the phrase does not have much to say about it. But so you can still opt to do a word cloud just to look at the distribution of the words within that column. So most of the words that have come out are story, of, good sense, our, perspective, distort. So these are basically the distribution of the words that you have within the phrase column. So I think we can leave that at that, because after that we're going to start building a model from it, which is something very little. So we can do that bit when we come back from lunch break, because this meeting has to end.
Okay, thank you. So we can go ahead and take the break now. We'll come back to complete the natural language processing, then do, pardon me, then do a short quiz on it before completing this module on data science with the data science lifecycle that Ernest is going to take us through. So let's now go on break. We'll be back at 2:15 to proceed.